In our next section, we're going to look at using EIGRP as the PE to CE routing protocol in a Layer 3 VPN. And we'll see that there are some special behaviors with using EIGRP for this application that extends the loop prevention mechanism of EIGRP and the feasibility condition over the MPLS network so that we don't have to potentially run into issues with multiple redistribution points. Now, in our very first example with this, we're going to look at a singly attached customer. Same as we were looking in the previous example, where when we were having router 9 attached to router 7 has this configured currently as VRF1, and we have router 10 attached to router 8. Router 8 likewise has this attached as VRF1, and then we're doing our VPN v4 BGP peering between the loop access 7 and 8, and then we also have IGP plus LDP in the core in order to complete the end-to-end label switch path. So again, with the rest of variations here in L3 VPN PE to CE routing, we don't really need to talk about the core anymore, because once that is set up, the only thing that is varying in the config is just the protocol that we're using on the edge. Now, we're going to look at this configuration in two different variations, one using the classical EIGRP configuration, the autonomous system mode, and then one using the named mode or the multi-AF mode. So between router 7 and router 9 on the left, we're going to use the classic mode. Between router 8 and router 10 on the right, we're going to use the named mode. Now, from the customer's point of view, again, it doesn't matter what or I should say, not that it doesn't matter, just that the configuration is a normal EIGRP config. There's nothing to do with VPNs, there's nothing to do with VRFs. On router 9, we would simply say something like this: router EIGRP1, network 0000. So we're just enabling the process on all links. And now, from the provider's point of view, we need to specify what particular routing table the EIGRP process is running in. We're on router 7. If we look at the show VRF, specifically the VRF's name is 1, and the VRF is assigned to interface gig 1.79. So this means that when we start the EIGRP process, we'll say router EIGRP1, we specify that the address family is IPv4, and the VRF is VRF1, and the autonomous system in this case is 1. Now, you'll see that some particular versions have problems with this syntax, which is the reason that, or at least part of the reason that they moved to the named format or the multi-AF format, where some of them will take this command in multiple lines, some of them will take it in single lines, and when you're using the classic mode, sometimes the process is a little bit unpredictable whether it will actually install the routes from the topology to the fib, and that's when you have to clear out the routing table, where you would say clear IP route VRF1 star in order to force the routes to download from the EIGRP VRF topology into the VRF rib. But here, once we go under the AS, the rest of the configuration is the same. We can simply say network 0000, and that's going to enable the process everywhere. So we can see now we have an adjacency, but now the adjacency is inside the VRF. If we show IP EIGRP neighbors, we can see that for the global table, we don't have any neighbors, but if we show IP EIGRP VRF1 neighbors, we have an adjacency inside of the VRF table. If we look at the show IP route EIGRP, globally we do not have EIGRP routes, but if we show IP route VRF1 EIGRP in the VRF table, we do. So we can see it's not that big of a change here from the classic process to the VRF aware mode. It's just that we specify the process globally. We give it any arbitrary number here, where technically the number that I used here does not need to match the autonomous system for the VRF, because you can use the same AS multiple times because they're unrelated instances of EIGRP. They're separate copies of the control plane. It's just that when we look at it from a syntax point of view, they're grouping them together under one configuration mode. So if you were to look at this at an actual process level, there's multiple copies of EIGRP actually running on the back end. Now, from the named mode, the configuration logic is going to be exactly the same, except we use the named configuration as opposed to the autonomous system mode. So on router 10, we would say something like router EIGRP A, and we have address family IPv4 unicast for autonomous system 1, and then we have EIGRP enabled on all of our links. Now from the provider edge side, we'll say the same thing. We'll say router EIGRP A. But now the address family is for the IPv4 VRF. And in the VRF, we're in Autonomous System 1. Okay, likewise, the network statement is going to go under there. And then anything else that is specific to EIGRP would go under things like the AF interface under the named mode, or it would go under the topology. So if I want to make a passive interface, if I want to do summarization, if I want to do an offset list, again, those go under the global process now, the named process, as opposed to going at the link level. But when you compare these configurations, they're nearly identical, with the exception of that this number here is talking about the global routing table's autonomous system number. This one here, we don't have an instance running in the global routing table. So if we show EIGRP IPv4 unicast, show EIGRP address family, IPv4 unicast, autonomous system 1. Let's say topology. The topology doesn't exist. We would have to be talking about the VRF. So this is one of the differences here, that when we look at router 7 and say show IP EIGRP1 topology, there is an instance on router 7 in the global routing table that we're not using. So it's basically a waste of the control plane because we had to turn EIGRP on, but we're not using EIGRP globally. We're using it in the VRF. In the named process, it does not implicitly start the global process unless you actually configure that AFI. So again, most of the optimizations are on the back end. The only thing that we really see is just a minor change in the syntax. From behind the scenes, things like the feasibility condition, the actual adjacency establishments, that's changing this. That's staying the same. It's just that they optimize the way that the process, that you interface with the process. Now, from the actual routing point of view, when we look at the provider edge, we can see here, this is how we would check the topology for the VRF. If we show IP route VRF1, we can see that we're receiving routes from the customer. We can also see that these routes are internal. If we show EIGRP address family IPv4 VRF1 topology and then the particular route, like the route to router 5's, or excuse me, route to router 10's loopback, this is an internal route, and we can see that we know all of the individual vector attributes about the metric. Now our last step is to do the redistribution, because everything else is already set up in the network. The core is already running IGP plus LDP. We have the VPN v4 peering between the provider edge routers. We have the VRF configured to the customer. We have the PE to CE routing to the customer. The very last step is to exchange the PE to CE protocol into the VPN v4 update. Now from a BGP configuration point of view, this is the same exact as it was under the RIP process, where we basically just go under BGP and we say for that particular VRF, in this case VRF1, we're going to redistribute EIGRP1. We're talking about the AS number. Now under the EIGRP process, we would do the same thing, but now it's going to be under the named mode, where we would say under router EIGRP A, for the instance that is specific to VRF1, we need to do redistribution, and I want to say that's under the topology base, redistribute BGP 100. Same thing on the other side. So on router 7, we're going to go to the EIGRP AS, and we're going to say redistribute BGP 100. Under BGP 100, we're going to go to address family IPv4 VRF1 and redistribute EIGRP1. If we now look at the show BGP VPN v4 unicast all, we see we have the routes end to end. If we look at the specific route encoding now, and we're looking at this from router 7's perspective, I want to know on router 7, what are the details about router 10's prefix? So let's look at the show BGP VPN v4 unicast all 151.10.10/32. We can see that we have inside the extended communities, there is a special encoding now which automatically includes the EIGRP vector attributes. What this means from an EIGRP feasibility condition point of view is that when router 9 goes to do a calculation about router 10, it does not see it as an external route. It sees the individual vector attributes, and it can run a normal feasibility condition check on it. So on router 9, when we look at the show IP EIGRP topology, and we look at and actually we can see this is the problem here. The process is stuck. I need to go to the PE router and say clear IP route VRF1 star. It's basically a bug. You're not supposed to have to do that, but now it forces the routes to refresh. On the named process side, it should not have this problem. Actually, it did. Let's do the same thing on the other side. On 8, clear IP route VRF1 star. That forces them to populate. But now if we look at one of the individual routes, let's say 151.10.10/32, it's a regular internal route that we can run the feasibility condition on. So what this now means from a route path selection point of view, if we have a route through the MPLS network and then we also have a route through a backdoor link, like let's say we have MPLS as primary and we have DMVPN as secondary, or like a legacy point-to-point T1 or something on the back end, normally when you're doing redistribution, we know that EIGRP internal would be preferred over external because we have a difference in the administrative distance. But in this case, even though we are doing redistribution, and we can see this both on 7 and 8, if we look at the show run section router, we're doing redistribution of BGP into the EIGRP process, which in EIGRP normally would create an external EIGRP route. But now when we actually look at the routing table, this is an exception. So these still count as internal EIGRP, and then when we go to actually route the packets over the core, we should see that we're going to follow the label switch path. Now again, this is happening automatically, so there's nothing special that I did in the config on the PE router with the exception of just doing redistribution. So in much older versions, in version 12.0 and before, 12.0S I should say and before, or 12.2 mainline, before this EIGRP cost community feature was supported, you did have to do the manual encoding of the metric. So you would have to say redistribute BGP 100, metric 11111, or whatever you want, but in this case, it's automatic. It takes the delay and encodes it as an extended community for the delay. It takes the minimum bandwidth and encodes it specifically as an extended community for the minimum bandwidth. So then since we have this extensibility of the BGP process, it makes the calculation just that much easier. That we don't have to treat it as if it was a different portion of the network. We just encode all of the stuff in there as part of the extended communities. And it's these ones that start with 0 by 8800. Now what these actually mean, we don't really need to know the details about them, but if you correlate this, like you can see that's the MTU, this one is the delay, this one is probably the minimum bandwidth I think there. But somehow in here these are the EIGRP vectors, and then it automatically copies back into the internal EIGRP network when we go to do the calculation on the customer side. So for example, if we were to now take another link, and let's say that we add a link on the back end between a router 9 and router 10, and we're going to run EIGRP over the link. So let's say on router 9 that we have interface gig 1 910, actually let's say 109, that is in cap .1q 109, IP address 155.1.109.9, and on router 10 we do the same thing, interface gig 1 109, encapsulation .1q 109, IP address 155.1.109.10. EIGRP is already running on all links, so we can see they immediately establish an adjacency. And if now we look at the show IP route EIGRP, it says right now we're preferring to use the directly connected link between them. We're preferring to use the backdoor route, the 109. So from router 10, if we were to trace 150.199, we can see it's not going over the MPLS network. But if we wanted it to do that, the only thing that we would need to do is just to go to the backdoor link, so gig 1109, and just increase the delay. So just like a normal path selection change, since the delay is now already encoded in the update, we're not trying to choose a difference between the route type. We're only looking at the metric value. Now, we'll see in the case of OSPF, this becomes much more complicated because of OSPF's path selection rules of intra-area over inter-area over E1 over N1 over E2 over N2, regardless of what the metric or regardless of what the distance is. But in the case of EHRP, since we're encoding these both as internal routes, the only thing we need to do is just affect the feasibility condition, and we would choose one route over another. Now, likewise, we could also engineer feasible successors here. That we could say from router 9's point of view that my link to the MPLS network is primary, and the link on the backdoor is the backup link, and this is the feasible successor, and then we can install both of them in the table if we wanted to do IPFast reroute. Because again, they're both counting as internal EHRP, so there's nothing special that changes about the path selection rules. Now, the same is true if we had multiple sites and we were doing redistribution on both sides and we were going to a remote site. So, for example, if we were now to introduce, let's say, router 2 into the EHRP network, and we run EHRP with router 3, and then we add router 3 as part of the VPN v4 peers, there's never a chance in this particular design that EHRP will cause a loop, because the feasibility condition now extends over the MPLS network. And it would say if I redistribute the route from EHRP to BGP and it comes back, it will always come back with a higher advertised distance. So I would always prefer my normal internal route over the MPLS network, and I just look at the normal feasibility condition. In other words, if my metric is 10 and your metric is 20, you're not loop free because you're further away than I am. So as long as we can encode those automatically, there's really no special behavior behind it. So again, they tried to basically just make it plug and play where you just turn the protocol on, do the redistribution at the edge, and everything happens automatically. And then if you did want to do traffic engineering like I did here on router 10, the only thing that we need to do is just affect the individual vectors under the EHRP topology. So if we show IP EHRP topology for 150.199/32, we now see we have multiple routes. One of them is a metric of 329 million. One of them is a metric of 655 billion. So of course this one gets excluded and we say this is going to be the successor. And then we look at what's the advertised distance. If we see that this one here, 327 million, is lower than 329 million, it does mean that this is a feasible successor. So on router 10, if we were to do this and go under the EHRP process and say under AS1, under the topology base, we want to do fast reroute per prefix, and we'll just say all. If we now show IP route for 151.99/32, we see that we also have our repair path because this is already a feasible successor. So in this case, if we were to track the provider, like run bidirectional forwarding detection, and then the link to the provider goes down, we would immediately update the pointer in the fib and not have to do reconvergence. So these same type of convergence techniques that we talked about previously in internal IGP, you can extend them when you're running MPLS with an L3 VPN provider, assuming that you run BFD with the provider. Because in 99% of the cases, you don't have a physical link to the PE. You have a link normally like to a Metro E switch, and a Metro E switch is doing the layer 1 keep alive. So if the circuit goes down, your router locally is not going to know about that. So you still need some sort of upper layer mechanism in order to do the signaling, and then you could fail over to your backup link, or like in this case, we're failing to our backdoor link, which is the direct connect between router 9 and router 10.